So let's talk about the conservation of energy. Now, you've probably heard this whole theme of conservation before in science. You hear about conservation of mass in chemistry. So we have to have the same amount of reactants that we do products because mass cannot be created or destroyed. Later this year, we'll talk about conservation of momentum as well. Now, the law of conservation of energy states that energy cannot be created or destroyed, it only changes forms. Of course, sometimes we say that energy is lost due to friction or something like that. But again, in that kind of scenario, it's still just changing forms because we might have a box maybe sliding to a stop on the floor. It has kinetic energy and then it slides to a stop, so it loses that kinetic energy. But really, what's happening is that kinetic energy is being transformed into heat energy, heating up the molecules on the floor due to friction. So the example that we have here on the screen is that we have a cannon that has gunpowder in it that then has a chemical reaction, and that chemical energy becomes kinetic energy when the cannonball shoots out of the cannon. As that cannonball then rises up, we know that it slows down a little bit because it's losing kinetic energy, and that kinetic energy is being transformed into potential energy. And then as it falls back down toward the ground, it's losing potential energy, but it's gaining kinetic energy. So it's speeding up as it goes back down to the ground. Now, some people might say, okay, well, it's losing all of its kinetic energy at the very end when it hits the ground. But what's happening here is that kinetic energy is being transformed into sound energy, so the noise that the cannonball makes when it hits the ground. And also, it's been being transformed into heat energy. So as that object is being impacted on the ground, that ground is heating up because of it. So the whole thing, we have to include the entire system. So we include the ground as well. And in that entire trajectory, energy is not created or destroyed. It's only changing forms. Now, here's another example. We have a bow and arrow, right? So we are able to pull back the arrow in the bow, and we're giving that bow potential energy. Now, when you pull that arrow back, we're doing something called work on the bow. Now, the way that we are able to do work on this bow is because we have chemical potential energy within us because of the food that we eat. So that chemical potential energy is then being transformed into kinetic energy as we pull the bow back. And then that is transformed into potential energy, elastic potential energy of the bow. We then let go the bow, right? And it shoots the arrow forward. So that potential energy becomes kinetic energy. And then as the arrow hits the target, it stops. But that kinetic energy is transformed into, again, sound energy and heat energy. So again, in this process, energy is still conserved. Another example here is we have something like a little wind-up car. So if we wind this up, we can get 10 joules of potential energy. But again, some people say, okay, some of this energy is being lost to friction because you're only getting 8 joules of kinetic energy out. But again, that friction is being transformed into heat energy. So again, you still have 10 joules of potential energy in and 10 joules of energy coming out. So again, if we include the ground and all of the surroundings, then energy is not lost. It's just transformed into different types. Another example here is a little bit more of a morbid example, but we have someone falling out of a burning building, and don't worry, the firefighters catch them at the bottom. At the very top, we have all potential energy, and we're not moving yet, so no kinetic energy. And then as that person falls down, they lose potential energy, but they gain kinetic energy because they're decreasing in height, but they're increasing in velocity. So we can see here that at the very bottom, they have 10,000 joules of kinetic energy. So all of that 10,000 joules of potential energy is transformed into 10,000 joules of kinetic energy. And every step along the way, the total energy is still going to be constant. So if you add up these two, potential energy plus kinetic energy, you still have 10,000 joules of energy. So this is the whole point of this conservation of energy, is that the total energy remains constant. So because of this, we can do a calculation with this stuff. So our conservation of energy equation is that the energy initial is equal to the energy final. So if we don't have any non-conservative forces like friction in which energy is dissipated as heat, we can use this equation here, kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. Now we might have gravitational potential or elastic potential energy or both. So you have to make sure that you include all of these things. Also, you might not have kinetic energy or not have potential energy in one of these cases. In that type of situation, all of the energy would be in one form or the other, or a combination of both. So it really just depends on the scenario. So, with every single one of these conservation of energy problems, you want to write down this equation and then plug in the other equations that you know for kinetic energy and potential energy, depending on the type of energy that you have in the specific problem.